Just a second, share my screen. Can you hear me? Can you hear me?
Yeah.
Yes.
Okay, yeah.
Well.
Okay, thank you. So, hello everyone, I'm Giulio Passerotti. I recently completed my PhD in ocean engineering at the University of Melbourne, and now I work as a research fellow in computer science, where I'm continuing to explore the use of computer vision for polar regions. Today's presentation is titled What Images of Sea Ice Tell Us About Marginal Ice Zone. And so to start, a brief introduction on sea ice. Sea ice plays an indispensable role in regulating Earth climate, and variation in ice condition and extent affect the environment, wildlife, and human activities, and they are closely linked to climate change. This variation are more intense in the marginal ice zone than a dynamic area between the open ocean and the continuous ice cover, which is characterized by the presence of ice floes that are floating pieces of ice. Here, the flow formation and ice breakup are strongly influenced by waves. In turn, the wave energy is dissipated as the waves propagate through the ice floes. Size of the flows and ice concentration affect the albedo, in general, the energy exchange between the ocean and the atmosphere. Okay. So due to the importance of these ice flow characteristics, the climate modelers have integrated these parameters in the sea ice models, instead of assuming a constant size and concentration for the ice. Unfortunately, the Southern Ocean is one of the most underobserved regions in our planet, making it challenging to build a comprehensive field dataset of sea ice properties to validate these models. And most of the field ice observation available at the moment are based on visual observation from ships or infrared from satellite images. And visual observations are subjective and depend on the experience of the observer, while the satellite is not feasible on a small scale of a few meters that is typical of the ice in the marginal ice zone. And even when close-range ice images are available, accurately detecting and measuring the flows is a challenge. So to overcome the lack of data and knowledge, we developed the Ocean, Sea Ice and Atmosphere Underway Observatories aboard the Australian research vessel Nuina, which is also recently returned from one of the Antarctic mission. And this system consists of a series of cameras with different types of optical sensor that continuously monitor vast regions of sea ice, providing high-resolution spatial and temporal data. And specifically aboard the Nuina, we have two synchronized stereo cameras to extract the surface elevation and track the evolution of waves, an optical zoom camera to measure the ice thickness, a sea ice camera to determine flow size, ice concentration, and ice type, and an infrared camera and two multispectral cameras to study sea and ice surface temperature, snow cover, and the presence of microorganisms. So this season is currently fully operational in Nuina, but it was previously deployed as a prototype on the South African icebreaker Agalas 2. And in the next few slides, I will focus on the images acquired from the Agalas and the image segmentation methods we use to obtain the visual properties of sea ice. So I will present you the post-acquisition steps like perspective correction, which are needed to measure the flows using a real-world unit. And then I will compare the results obtained using traditional image processing methods, artificial intelligence techniques, and a combination of both. And finally, I will analyze the results obtained after segmenting the full dataset collected during 3 Antarctic winter expeditions. So after the acquisition, we need to correct the perspective since the images are geometrically distorted. And to do that, we need to know the camera matrix. And the camera matrix consists of intrinsic parameters that are focal length, optical center, and pixel size in word units. And these parameters affect how the image is formed. and then the extrinsic parameters that describe the camera spatial position and orientation. So the intrinsics can be estimated with a chessboard through the camera calibration process proposed by Zhang. And this method is based on the correlation between the square corners of the chessboard and the corresponding 3D world coordinates. And while the extrinsic parameters are directly measured aboard the ship. So here is the orthorectification for a sample image on the upper left with known elevation, tilt, roll, and heading. And in this case, all the angles and elevation are assumed to be constant throughout the cruise. And on the right is the image corrected with a resolution so that 1 pixel is equal to 0.05 meter. And as the boundaries of the flows lose sharpness over distance, we limit the analysis to an area of 7,000 square meters. And after that, we applied a series of filters to enhance the image quality. And these filters are adaptive, so meaning that a predefined threshold is not required. And this filtering helps to improve the performance of the image segmentation techniques. So it will be the starting point of each method. However, it should be noted that we consider the camera rotation angles and elevation as fixed during the orthorectification, despite the effect that ship motion has on these parameters. We did that because we conducted a sensitivity analysis where we adjust the angles from the condition of calm seas to the extreme values recorded during a storm in 2017. And the analysis revealed that the impact on the flow size was less than 5% for each parameter. That is the blue shaded area in the graph. So considering also the challenge of associating the ship's movement with each camera shot, this error margin was considered acceptable. So now we can start with the study of the detection techniques. And several image segmentation methods can be found in the literature. And the most used are thresholding, watershed, and K-means. Each of these techniques presents some issues. In particular, threshold are too subjective. Watershed leads usually to over-segmentation. And K-means is constrained by the number of clusters chosen. So these problems are partially solved by applying the gradient vector flow snake algorithm, successfully reported by Zhang. And the gradient vector flow snake model is a segmentation method that evolves an initial curve within an object toward its boundary until it matches the perimeter of the object itself. So a proper contour is still required to initialize the model. And so here is presented a generalization of this method for detecting ice flows under different level of image clarity. So starting from the enhanced sea ice image, so the first step is binarize the image and estimate the sea ice flow seeds with the distance transfer matrix. So the distance transfer matrix is the matrix of the distance between each pixel and the nearest 0 pixel in the background, while the seeds are the local maxima of this matrix. And these seeds are effective at pinpointing individual ice flows. Then find the contours of sea ice flows that are well spaced from their neighbors in the image. So these are the white regions that contain just one seed. And for these flows, the segmentation followed the binarization. Then we construct an elliptical contour for the flows with only one seed, following a morphological erosion. And the morphological erosion allows to isolate the seeds of those flows that are connected to others by just a few pixels. Then we construct a circular contour for the remaining flows, which share a significant portion of the edge with their neighbors. And in this case, the values of the distance transfer matrix corresponding to the unused seeds are chosen as the radius of the circular contour. So after this, we segment the ice flows as a result of the image binarization. Then we segment the ice flows by initializing the model with elliptical contours and after with the circular contours. In the end, we remove anomalies and combine the preliminary results. So inaccuracies and flows connected to the body of the image are removed, and the finally binary mask of all the detected flows is obtained. However, image segmentation has experienced deep transformations due to the recent advancement in artificial intelligence. And new deep learning algorithms are able to learn how to identify objects in the images relying on a training dataset. A training dataset is a broad collection of images where the object of interest are labeled. So, for polar regions where training data are scarce and difficult to obtain. However, these models permit to minimize the user intervention and reduce the computational time. And so the few studies in the literature that employs deep learning for CIS detection are mainly based on semantic segmentation that recognize but not segment the individual flow units, or in other cases are limited to just the classification of different types of ice. So vision foundation models instead are deep learning models trained on a massive amount of data. So as a result, they perform efficiently for instance semantic segmentation, object classification, and detection across different domains. So they serve like as a general purpose system. And segment anything model, SEM, by Meta is the first vision foundation model capable of segmenting a familiar object in an image without additional training data. And this model offers two modalities, automatic mask generator and prompt-based mode. The first modality is designed to independently segment every recognizable element in the image, while the prompt-based mode allows the user to guide the segmentation by marking regions of interest with points. So here the performance of SEM for detecting CIs is explored using both modalities. And so with the automatic mode, SEM selects a fixed sample of points in a grid over the image. And for each of these points, it generates one or multiple segmentation masks corresponding to the identified object. And the output is a list of masks of all the elements in the image. So in our case, this list includes masks of flows and open water regions. So as for the previous method, the snake model, we perform a filtering to discard inaccuracy and undesired mask. Then the list is consolidated into a single comprehensive mask to eliminate the mask redundancy. The mask redundancy primarily occurs with adjacent or overlapping flows that have poorly defined boundaries and for which the model generate more than one mask, so alternative mask for the same flow. Okay, in the prompt-based mode, the user selects the prompt needed to initialize the model. In our case, we decide to use the same seeds obtained with the snake model. And so the result is a list of flow masks with one mask, in this case, one mask generated for each seed. However, introducing a seed in a low clarity area of the image may result in the generation of inaccurate masks that include discontinuous water region or parts of adjacent flows. So the masks that don't match the typical shape of ice flows are filtered out by the shape-based filters, while masks relative to portion of a flow are corrected with the mask consolidation. So during the application of SEM, we discovered that the segmentation of adjacent flows with weak edges can be further improved by incorporating knowledge of the ideal flow shape in the model. So this can be achieved by adding a step where the flows are processed by the snake model, in which in the snake model, the initial contour represents the shape information. So the workflow of this hybrid approach starts again from the finding of the seeds. Okay, so however, in this case, the distance transfer matrix is computed on the unified mask obtained from the SEM prompt mode. So as a consequence, most of the ice flows are already correctly detected, and the initial contours are generated just for the remaining part. Then the snake model is initialized with those contours, and the results are filtered and combined together. Okay, so the algorithm that can serve as an objective standard of comparison. So we select several images with different levels of sea ice clarity to create a benchmark segmentation. And this benchmark segmentation is conducted using photo editing software, the contours of the flows in the image. And then the binary mask of each flow can be used to measure the flow size parameters. On the left, we have the boundaries of the flows superimposed on the original images to highlight the segmentation, while the figure on the right shows the flow size distribution for a sample image with it's important to note that for nighttime images, the manual segmentation is limited to the areas illuminated by the ship's light. So after the creation of the benchmark dataset, we applied all 4 segmentation methods to the benchmark dataset, and we extract the flow properties, and then we compare the statistics to those derived from the manual segmentation in order to assess each method's performance. So in the upper panel of the left figure, we compare the number of detected flows and the ice concentration with all values normalized to the manual benchmark that is represented by the horizontal line at 1. So we can observe that Snake and SEM in automatic mode underestimate the flow count, while both SEM prompt mode and the combined method approximately match the manual segmentation. A similar result is observed for the ice concentration, but in this case, SEM automatic mode improves its performance, while the Snake is still the worst because it underestimates with an error of around 20% the ice concentration. In the middle panel, we present the violin plots of the flow size based on the diameters. And Snake and combined method here capture the overall shape of the distribution, while SEM in prompt mode closely align with the benchmark shape, but underestimate the smaller flow size. In contrast, in this case, SEM in automatic mode produce the least accurate distribution. And these results are confirmed in the lower panel, where the QQ plots at 10% intervals are shown. In this case, the closer the values fall to the solid line, and the closer the size distribution is to the benchmark. However, declaring with just this graph 1 meter superior to another in absolute terms is impossible because the choice of the model to use depends on the specific use case, time constraint, and available computational resource. So the figure on the right is a visual comparison of the segmentation results for a sample image. And the left column shows the original sea ice image with the segmented flow contours overlaid in red for each method. And while the right column highlights the differences between each automated method and the manual benchmark. The errors are typically three categories. So we have the missing flows in green. There are flows that are present in manual segmentation, but they are not detected with the automatic methods. Then we have the misinterpreted flows in yellow. There are partially or incomplete segmentations. And then the hallucinations in pink that represents false positives. So they indicate patterns or textures that are mistakenly detected as ice flows. So after evaluating the different methods, we decide to extend our analysis to the entire data sets of ice images. In this case, we use the snake method, which provides good results for the flow size distribution as seen before. And the field dataset was acquired during 3 winter expeditions to the Antarctic meets in 2017, 2019, and 2022. These expeditions were part of the Southern Ocean seasonal experiment scale with the South African research vessel. And the tracks, the ship tracks, on the right. And overall, we spent 1 day in ice in 2017, 3 days in 2019, and 6 days in 2022. And the right figure also shows a zoom for each expedition, providing an overview of the flow size encountered during the voyage. And the black squares represent areas of compact ice, while the ice concentration is from the satellite. So from this figure can be observed as during the second voyage, the ice was encountered souther than indicated by remote sensing, and norther during the third expedition. So this figure shows the flow size distributions divided by year and compare with the distribution of significant wave heights outside the marginal ice zone during July, extracted from satellite data and calibrated by IMOS. So comparing the flow size with the wave data helps to highlight the heterogeneity of the ice across different years against a relative constant wave distribution. So from left to right, we have the probability density functions of the flow diameters and the wave heights, with a vertical black solid line representing the mean significant wave height. So in this case, the solid line is for flow size and the dashed line is for waves. Then next, we have the exceedance probability and the QQ plot for the 10th, 30, 50, 70, and 90 percentiles, where the solid black line represents the perfect equality between the wave and the ice distributions. And in the end, the column on the right shows a typical image of the flows encountered during each expedition. So it should be noted that the distributions of flow diameters are not presented chronologically, but are arranged to reflect the different states of sea ice formation. So this because in 2019, the icebreaker, we encountered the sea ice during the initial stage of flow formation. As you can see from the image, the typical image of ice, the flows have a round pancake-like shape, and we have a relative uniform diameter distribution. Moving on the 2017 formed, this is also due to the interstitial solid fragile ice that constrain further growth in size. And this leads to a broader probability density function. While in 2022, we observe an even more pronounced trend towards larger flows, with many images that recorded. And these characteristics are not typical of pancakes, but are indicative of broken or brush ice. And this supports the hypothesis that the flows during this year, 2022, resulted from breakup events. And in general, we can see as during the initial phases of ice formation, the flow size distribution mirror the wave distribution, and then they diverge when the pancakes start merging together in larger flows. And the differences in size between the various years become more evident when we combine the exceedance probabilities into a single graph. And remembering that the images were acquired in the same season and the same month, we can observe that the ice is not uniform, but is in continuous evolution, merging, breaking, and merging again. So, in conclusion, with this study, we established a precise methodology for image acquisition, including camera calibration and perspective correction to measure the flows in world units. Then we compared the snake models with vision foundation models, and what emerges is the robustness of traditional segmentation against the flexibility of deep learning models. We propose a novel combined approach that couples the shape-informed segmentation of snake with the scalability to complex ice scenarios of SEM. And in the end, we have shown that small-scale changes that sea ice undergoes during winter, changes that never been observed before, and they are difficult to detect using satellite images. And this demonstrates the great heterogeneity of sea ice in the marginal ice zone. Thank you for the attention.
Thank you very much, Giulio. This is a very nice presentations with deep learning, AI related tools. Is there any question or comments? You can proceed. Any questions? No. Okay, Giulio, you have mentioned there is a frog and you mentioned deep learning methods and
Yeah.
means collocation something. Can you please clarify that point one more time?
I mean, now it's sending us on some weird paths.
Which one?
That's all right.
No, where you mentioned, yeah, before slide. Yeah, here.
Okay. Okay.
Should have used Apple Maps.
To explain more in detail this slide.
Probably was telling us that way. Yeah.
Okay, so okay, technically we have.
I'm always confused here. Hey, sorry.
Okay.
I want to ask a question.
Yeah. Okay.
What's the next step in this work, do you think? I know you're not involved in it maybe yourself, but how would I'm wondering how you to take this work further.
Okay, yeah, the next step of this work, okay, for sure one of the steps will be to go further. So now we can segment the pancakes or round shaped ice, and even more like rectangular shapes. But the next step definitely will be to be able to identify the different types of ice. So at the moment it's more focused on pancakes, but the next step will be to be able to identify, for example, fragile ice, brush, consolidate, and even if the flows are covered by snow or not. Yeah, and this kind of stuff. Yeah.
And the system's working, like the cameras are going to be permanently mounted on the ship, is that right?
Yeah. On the Nuina, they are already fully operational, and these are the. Can go back. Yeah. Oh, too much. Okay, we have all these cameras.
Okay, and the system's quite reliable, is it? Because it must be a tough environment for those cameras to work.
No, it's quite reliable. I mean, need to be supervisioned by someone, but yeah. I mean, we use this system as a prototype in the during the Antarctic missions with the colleagues of the University of Cape Town over 3 different years. So we have some knowledge, and now the system on the Nuina, the Australian one, is more robust and reliable. Yeah.
All right, thanks very much. Thanks for your talk as well. It's great. Sorry, I don't know if I interrupted the question there for some, but thanks a lot.
So, thank you, Giulio. We have to proceed further. Thank you very much.
Thank you.
You can stop your
Close.
screen sharing.
Yeah, sure.